Yes? Okay, so let's find the x-intercepts first. So in y equals, let's put the function in and try to find the x-intercepts. Y equals, clear if you have anything else in there. And the function was x cubed minus 12x plus 2. And I will, So I would go to second in calc, and I would find the zeros. As you see, there is a problem here. Oh, that was something else. I was just going to say that the calculator is fooling us. I guess it is not. She is not. Okay. So I want the zeros, and I see I'm cheating because you don't have this window unless you already graphed the function. I see 3 solutions as expected. So I'm going to determine this. 1, 2, 3, 4, 5. So between -5, left bound -5, positive bound -4, and I have to start again. So I guess the 0 would be between -4. Okay, -4 and -3. Yes, I don't want to guess. Just give me the number, please. And it says -3.5. And it's 0. Okay, the other solution is between 0 and 1. So second in calc, another 0, which is number 2, between 0 and 1. Give me the solution, 0.17 and 0. And finally, 1, 2, 3, 4, between 3 and 4. Second in the calc, I want the 0, between 3 and 4. Yes, and I want 3.4. So 3.4 and 0. So I have everything I need. Of course, the function is not symmetric. I have to write somewhere that f of -x does not equal f of x, and it does not equal -f of x. Not symmetric. And now we're ready to graph. Although we saw the graph, but we can do everything by hand right this moment. We don't care about anything else but the table. I'm going to graph it on the next page because maybe I should do this. I'm going to do this. Okay. That's all I care about. I don't need anything else. A -3.5, comma 0. 1, 2, 3, 4, 5. So 1, 2, 1, 2, 3.5 right here. Then -2, comma 18. So the high goes to 18. I'm going to say 5, 5, 5, 5. So this is my 18 at -2. Then I have 0, 2. And then I have 2, -14, 5, 5, 5, -14 at 2. And then I have 3.4, 0. So I plotted all the points. So now it's coming from -infinity, opening downward and increasing to the local max. It's coming down to 0, 2, which is an inflection point. Then it continues to decrease, but this time opening upward till the minimum of 2, -14. And then it continues to increase. It crosses the x-axis at 3.4, 0, and it goes to infinity. There are no more secrets here. X cubed minus 2x plus 2. And we knew all this from the table. It was increasing, it was decreasing, and increasing, opening downward, the inflection point 0, 2, the minimum 0, negative 14, the maximum negative 218, and these are the X-intercepts. Questions?
Is x cubed minus 2x or minus 12x?
Thank you. I'm hungry. No excuse. Very good. Any questions? This was problem 33 on page 299. We looked at a problem. I want to make sure again. What was it? I think you picked the absolute. I think you picked 28, right? We did problem 28 on 298, correct? The one with an example of the graph in which we put everything together after we summarized it. Yes? Was it 28? Can anyone confirm, or I'll go back and look?
Number 17 on 298.
We did 26. Okay. Okay, so is that good enough? Do we need another example?
Yes.
Yes?
Yeah.
Very good. Okay, so let's choose another example of a function that fulfills the given conditions. And then I would like to graph another function from scratch. So we did 26, correct? Okay, so please choose another. If you don't, I will. Okay, I'll choose 28. Is that okay?
Yes.
Okay, 28. So let's work on 28. On page 298. So we have f prime. It will take me 15 minutes to just write the information down. I'm kidding. So f prime of x is less than 0 if the absolute value of x is greater than 2. F prime of 2 is 0. Limit of f of x as x approaches infinity. F of negative x equals negative f of x. Then f double prime is less than 0 for 0 and 3. And f double prime is greater than 0 for x greater than 3. Okay. We have all the information. We will need to summarize the entire thing in a table. Once we summarize it, then we will be able to graph. Once I summarize it, I can check them out or whatever. Okay. So here's x. Here's f prime. Here's the function. And here's f double prime. From negative infinity to infinity. Okay, I will start with the easiest part, which is this. The limit of f of x as x approaches infinity is 1, so this is done, which automatically means y equals 1 is a horizontal asymptote at infinity, maybe at negative infinity. I can put it in, I can consider it, but it doesn't matter. That's what's given right now. It's a horizontal asymptote at infinity. Done. What does this say to us? That f of negative x equals the opposite of f of x. What does that mean? Always, for any function. The other one, exactly. So the graph, this is an odd function. In other words, the graph must be symmetric with respect to the origin. So if that's the case, then I know that at the other end it cannot have a horizontal asymptote y equals 1. But it has a horizontal asymptote of if it's symmetric with respect to the origin. What do you think? So there is a y equals 1 here. Across the origin, it's going to be y equals -1. Very good. Y equals -1 is the horizontal asymptote at -infinity. For this reason. Very good. Okay, let's go back. What does this mean? We know what it means. We looked at it last time. What does it mean? The absolute value less than 2. It means that x is between -2 and 2. So -2 and 2. The first derivative is positive. And this is done. Also, what does this mean? The absolute value of x is greater than 2. It means the outside. Exactly. It means when x is less than -2 and when x is greater than 2. Not what is included here, but the outside. So it says it's negative. Done. Okay, f prime of 2 is 0. Okay, done with that too. We'll see in a minute, this function has to be symmetric with respect to the origin. So if it has a critical number at 2, it will have to have a critical number at -2 by symmetry. So that's all done except these two. Okay. The second derivative is negative between 0 and 3. Okay. 0 and 3. The second derivative is negative, which means the function opens upward. That's done. And now the second derivative is positive if it's greater than 3, if x is greater than 3. Fine. I'm sorry. I got carried away. Of course. Very good. But this function is symmetric with respect to the origin. So if it opens upward here, on the other side, between -infinity and -3, has to open downward. So it's negative by symmetry across the origin. And of course, if it's opening downward between 0 and 3, it must open upward between -3 and 0. So obviously -3 can be considered, and 0 and 3 can be considered inflection points. So IP, IP, IP. Obviously, whatever these numbers are, I don't have them, but definitely this is a local min right here at -2, and this is a local max right here at 2 comma whatever, but they have to be symmetric across the origin. So if you put here if you put here, let's say 2, it's a maximum, then you have to put here -2. So it took us a long time to summarize the information. So now let's come up with an example of such a graph. And then we can go back through everything and check that we did not miss anything. So first I have to graph the asymptotes. So there is a horizontal asymptote at 1. And there is a horizontal asymptote at -1. Okay. So the function has to decrease to this -3, 0. Oh no, it's -3. I don't have a number. And 1, 2, 3. So this is -2, -3, 2, and 3, and this is the origin. At the origin, the function has to have an inflection point, and it has to be here because otherwise it will not be symmetric with respect to the origin. Okay, so let's see what we have. So it's decreasing from -1 to an inflection point, and then all of a sudden it changes concavity and it goes to a minimum. So I'm going to graph this. That's my choice. So at -3, it opens downward. It's decreasing from -1 to whatever, and continues to decrease to -2 to whatever. Opening upward, careful. Opening upward. It changes concavity there. So it continues to open upward, and it goes to the origin, where it changes concavity. I don't care for the rest of the table. I don't need it. It has to be identical on this side. So it has to increase to this point at 2, and it has to decrease to 3, whatever, this point. And right here it has to change concavity and approach the asymptote. So now we can go back and double check everything. It's positive between -2 and 2. It's increasing, yes. Between -2 and 2, the function is increasing. It's decreasing outside, yes. Decreasing outside. Decreasing outside. F prime of 2 is 0. Yes, it's a critical number. It's a maximum or a minimum, respectively. The limit, yes, it is 1. This part has to be -1 because it's symmetric with respect to the origin. Is it an odd function? Yes, it is. The second derivative is negative between 0 and 3. Yes, between 0 and 3, opening downward. On the other side, it has to open upward. And outside, it opens upward. And the other side has to be completely symmetric with respect to the origin. So this is our f of x. Any questions on this? I personally highly recommend create a table. If you don't like my table, that's fine. It's not my table. I'm not going to take credit for it. But I was taught this way, and I think it makes sense. But you can say, no, it doesn't make sense to me. I'm going to invent my own chart. Use your own chart. I'm fine. As long as you can put the things together, you don't have to use this. But please, I'm begging you, do not use something like this. I'll accept it, but it's going to be very hard for me to read it. And I'm hoping that you're not going to do this and just come up with a graph, because I will not be able to follow this. What is this? Yes, it's fine. They go through all the steps that are required, like we did. Okay, here are the steps. We're going to get to asymptotes in a minute. I'm going to show an example. Domain, of course. Intercepts, yes. Symmetry, yes. Asymptotes, yes, of course. That's a summary of curve sketching. Intervals of increase and decrease, of course. Local max min, yes. Concavity, points of inflection, yes. Sketch the curve, yes. But I have no idea. It feels like they just presented everything and they just copied the graph somehow. Okay, ready? So we're back to 4.3. We looked at a couple of examples in which we're asked to come up with a function. And I would like us to investigate one more graph, at least one more, from scratch, from the beginning till the end with the graph and everything. And then I would like us to look at graphs that rational functions with slant asymptotes. Okay, do I get to choose again, or you want to choose? We looked at this simple problem. It wasn't that difficult. Yes, we had some difficulties in determining the x-intercepts, and we may encounter difficulties like those. The other problems, but I would like to at least work on another problem from the beginning till the end. Or if you want more than one, that's more than one then. Any preference?
38?
38? This one?
Yes.
It's another polynomial function. So it's not that different from the previous one. So for example, something like this with rational exponents, or a radical problem, function, or a natural log. So let's illustrate with other types of functions. Only because we already did one polynomial. So would you like to look at the radical? Would you like to look at 40?
39.
We want to look at 39, the square root of 6 minus x. Very good. So let's do that. It must be something special that they put it in red, right? Okay. So 39 on page 299. So one more time, what are we doing in this chapter? In summary, in chapter 2, we looked at limits, right? And we said that limits took us to derivatives. What did we look at in chapter 3? Differentiation rules. We just learned to differentiate all sorts, right? From functions to products of functions, ratio functions, differentiating functions that we don't have a rule of differentiation using the log. What are we doing in chapter 4? We're looking at applications of differentiation. And what are those big applications here? There are 3 major applications. One, we're able to graph anything without the use of the calculator that we could not do before. What is the second one after this? It's going to be optimization. What optimization is, we're going to find max-min of functions in real-life situations. It's a big umbrella of math. There are a lot of 600-level courses on optimization of any level, and especially multivariable. Okay, what is going to be the third and the last application here in this chapter? Newton's method. So 3 big ones. How to graph from scratch to the very end, like we just illustrated, and this is another example. The second one, optimization, we did not get to just yet. And the last one is Newton's method. And I'll explain what Newton's method is. Are you okay? Are you okay? Okay, good. So here we are asked to show everything and graph this function. What is our first step here? Finding the domain. Excellent. So what do I have to write? Because I need to get my chart, my table going. And without a domain, I cannot even think of starting anything. Can anyone tell us what to write for this in order to find the domain? Excellent. Very good. So 6 minus x is greater or equal to 0. Negative x greater or equal to negative 6. Or x less than or equal to 6. Do we agree with that? Do we agree? Yes? That's all I need to see in the table, please. Nothing else matters. We're not interested in anything else but the interval between negative infinity and 6. Is this okay? Yes? Okay. So immediately I want to determine this limit. And I want to determine this number. So if I plug in 6, what do I get? 0. Very good. 0 has to be in the table as long as it's in the domain or somewhere in between. What is x? What is f of 0? I'm sorry. I meant to put it here. What is f of 0? 0. Very good. We haven't discussed the first derivative yet. Perfect. Okay, so now the limit. Limit as x approaches negative infinity from x, the square root of 6 minus x. When x approaches negative infinity, where does this go? Very good. Plus 6 doesn't matter. The square root of infinity goes to infinity. Where does this go when x approaches negative infinity? And how much is negative infinity times infinity? That's it. Great job. Perfect. Okay. There's nothing else I can find about the function from the function itself. I've exhausted everything. I have the x and y intercepts. I have limits. Done. Now I'm ready to study the first derivative. So f prime of x. The first function prime is 1 plus x times the second function prime, 1 over 2 the square root of 6 minus x. Please do not forget the negative 1, which is the inner function prime. Do we have this? Now, of course, I need to work on this expression. What is the least common denominator? 2 the square root of 6 minus x. What do I need to multiply the top of the first fraction? The second one is fine, it's negative x. But I need to multiply the top of the first fraction by 2 the square root of 6 minus x, which is 2 parentheses 6 minus x. Because when I multiply the square root of 6 minus x by the square root of 6 minus x, I get 6 minus x. Would you agree? I distribute now. 12 minus 2x minus x divided by 2 the square root of 6 minus x. And I get, with factoring, negative 1. So this is negative 3. So I factor out negative 3. So we had negative 3x plus 12. So this is x minus 4. Let's check. Negative 3 times x, yes, is negative 3x. Negative 3 times negative 4, yes, it's indeed positive 12. Okay, nice. I have the derivative. Now my next step is to find the critical numbers. Good, critical numbers. How do I find the critical numbers? So either f prime of x is 0 or f prime of x is undefined. Is this function ever defined where the undefined, where the function is defined? At 6. Very good. So then this is undefined at 6. And so is the second derivative. Perfect. So this is done at x equals 6. But what about when f prime is 0? Do I have anything coming from f prime being 0? Excellent. Great job. Immediately I need to determine this value right here. So please plug in 4 and tell me what you get. So it's 4 times the square root of 2, right? F of 4 is 4 to the square root of 2, approximately. 1.2 times 4 is 4.8. So approximately 4.8. Okay, so I have the critical number, or numbers in this case. What is the next step? What do I need to do next? I need to find and study the sign of the first derivative. Very good. Okay, so here's the first derivative. I refuse to even consider plugging in anything in what I shaded. Don't erase anything. Why I refuse to plug in anything in 3 over 2 times the square root? They will always be, yeah, I'm not going to waste my time. It's always positive. Why would I even worry about it? So I'm only interested in negative x minus 4. Negative x plus 4 if you want. So what is the sign of negative x plus 4 to the left of 4? Negative x plus 4 is a linear function that looks like this. What is the sign first? To the left of 4. Positive. What is the sign to the right of 4? That's it. Or you plug in numbers. Plug in 0, you'll see you get negative 4. You get positive 4 because it's negative 4 times negative 1 in front. Or plug in 5 and you see you'll get a negative number. Now this is the moment of truth. This is how I check my work. If these two rows work well together, I'm in business. If not, I have to go back and start from scratch. Okay, so from negative infinity to 0, what does the function do? Is that supported by the sign of the first derivative? Perfect. From 0 to 4.8. Good. From 4.8 to 0. Is that supported? Good. So now I continue with the second derivative. Any questions so far? Any questions? Is this okay? Yes? Okay. So second derivative. I really don't like it. So negative 3/2, do not worry about that. I'm not going to use it, of course, when I differentiate. I don't care for it. So when I differentiate a constant times a function, I differentiate the function, of course. Negative 3/2. Leave it alone. Don't include it. You're going to make your life more difficult if you do. It's a constant. It's a factor. It can wait patiently. So the top prime is 1 times the denominator minus the top times the denominator prime times the inner function prime over 6 minus x. So always try to simplify as much as you can the expression before you attempt differentiating it. I don't want that 3 or negative or 2 in there. They can wait. Questions so far before we continue? Okay, it's a lot of work here. The least common denominator in the numerator, please. Again, to the square of 6 minus x. This one still needs a 2 to the square of 6 minus x. I will have again 2 multiplied by 6 minus x. And then this multiplied by negative 1, so it will be, so this is negative x plus 4, but it becomes positive x minus 4. This is 6 minus x over 1, and I have to flip that. And I get negative 3/2 times 2 6 minus x, the square root of 6 minus x after I flip the denominator. And the numerator is 12 minus 2x plus x minus 4. Okay, so this is negative 3/2, and this is negative x, and this is positive 8 over 2, 6 minus x, the square root of 6 minus x. Of course, I'm going to pull out a negative 1, so I have 3/2 x minus 8 over 2, 6 minus x, the square root of 6 minus x. After all this work, I managed to determine when f double prime is 0. When is f double prime 0? Only at x equals 8. But that's beautiful. That's awesome. I worked for 10 minutes to realize that 8 is not even in the domain. Awesome. It's okay. No problem. So then I need to find the sign. So I refuse to plug in, before 6 minus x, we already said that from the beginning. I refuse to plug in anything in here. Why? Because we already set the 6 minus x to be greater than 0, and the square root is positive, and 3/2 and 2. I don't care about those. So I only need the sign of that. I know it crosses at 8, and it has a positive slope, so it's coming from negative 2. Good. But 8 is outside of the domain, so it's always negative. So this function always opens downward. It has no inflection points. So on the interval negative infinity to 6, the function is concave down. Perfect. What type of point is 4, 4.8? Local? Very good. That's it. That's all I care about, the table. Of course, it's not symmetric. It's, how can it be? It's only defined between negative infinity and 6. Zero, 0. 1, 2, 3, 4. 1, 2, 3, 4, 5. And 5, 6. Ready? So it's coming from negative infinity, constantly opening downward, increasing to the origin, and increasing to this point, which is a absolute and local max. Fine. Then it's decreasing to this point, which is 6, 0. And this is it. This is the graph of f of x, x the square root of 6 minus x. Any questions? How do we feel about all this process of graphing functions? Before we look at rational functions, we have not looked at any rational function, and we haven't looked at asymptotes. So it is the same process. They present the same steps, but it's all summarized in a table. We're doing the exact same thing. Any questions on this, or would you like to work on another, or can we look at a rational function now? What do you think? Yes, Ella, go ahead, please. You wanted to say something?
I'm tired.
Okay. I know that, and that's why I'm trying to kind of finalize as soon as we can so we can review, because I know moving forward there are 7 weeks left. Everyone gets bogged down and overwhelmed. Yes, of course, that's my next step anyway. Of course, of course. So that's why I'm trying not to leave important stuff and major stuff for the last day, because we need to review it. I know that, trust me. Everyone gets tired about this time in the semester, which makes sense. Okay, so let's take a look at a rational function. Let's start with a simple rational function. And then we look at one with slant asymptote. So here is a simple situation. X squared minus 2x plus 1 divided by x minus 1, x plus 3. I'm going to just put a 2 in front. Yes, this is a rational function. I have to get my table going. And what do I need? Before I even think of the next step, I have to have the first step done, which is domain. Please, can anyone give us a domain of this function? Very good. Domain cannot include -3, cannot include 1, because the denominator will be 0 at those points for those x values. Now we go back and we not simplify, but factor the numerator. So 2 times, can anyone give us anything about the numerator? Yes? Very good. Here's what happens now. Remember, we have to state restrictions on the raw function. We cannot simplify and then state restrictions. That's not possible. That's why we state the restrictions and then we simplify the function. What happens at x equals 1? It cannot be the same as what happens at x equals -3. It cannot be. At -3 is an asymptote. The factor cannot go away. But what happens at 1? So be very careful. X equals 1, it's a hole in the graph. X equals -3 must be a VA. So at this step, we have to determine everything about the function from the function itself, which is a lot, if you want. This limit, this limit, this limit, this limit, this limit, this limit, and what happens at 0. And furthermore, the x-intercept. It's a lot of work. Can anyone give us the x-intercept for this function? There isn't one. You would have said normally x equals 1, but the function is undefined at 1. So there is no x-intercept. Now let's find the y-intercept. 0, so this is -2, and 0 plus 3. So when x is 0, y is? Very good, awesome, -2/3. All I need to now is this. All those limits. Can anyone tell us the limit at infinity? It's infinity over infinity. Differentiate the top, differentiate the bottom. Okay, let's write it. Let's write it. So we have limit of 2 x minus 1 divided by x plus 3 when x approaches infinity. So this is infinity over infinity. We have exactly 2 situations in which L'Hopital's rule is applicable. One is 0 over 0, and the other one is good. So it's infinity over infinity. Let's say we don't remember from pre-calc, and we differentiate the top. What do we get when we differentiate the top? Times the 2 in front, which is 2. We differentiate the denominator. So what is the horizontal asymptote? 2. Y equals 2, horizontal asymptote. 2 and 2, y equals 2, horizontal asymptote. Very good. Now I have to find these limits left and right. Let's do it. So the limit as x approaches -3 from the left, limit as x approaches -3 from the left, from twice x minus 1 over x plus 3. You know it's infinity. Not here, though. At the whole, it cannot be infinity. It's going to be a number. I don't know which number. We'll see in a minute, but it cannot be infinity. So limit as x approaches -3 from the right, 2 minus 2 times x minus 1 over x plus 3. What do we have now? So when I plug in -3, the numerator is negative on both cases, but -3 from the left with -3.1. -3 from the left, -3.1. So plug in -3.1 in the denominator and give me the sign. Good, so the answer would be? Very good. Okay, so now let's plug in -2.9. The top is still negative. -2.9 for the denominator. Good, so the answer would be? Very good, awesome. One more step, we want to find this, left and right of the whole. So limit as x approaches 1 from the left of 2 x minus 1 over x plus 3, and limit as x approaches 1 from the right, 2x minus 1 over x plus 3. So what is it? The answer is for both. How much? How much? Yes, positive for the denominator, that's fine. Okay. Exactly 0. Exactly 0. So the whole is 1 comma 0. Very good, of course. 1 comma 0. We completely exhausted this. There is nothing else I can find. I found the limits, I found the asymptotes, or the asymptote in this case, I found the whole, I found the horizontal asymptote, I found the limits, there is nothing else. I found x and y intercepts when they exist, that's it. So what is my next step? I filled up the chart for f. What would be my next step? F prime. That's my next step. Very good. So let's find f prime. So one more time, f of x is 2. Do not bother with that. It's a number outside. You can wait. It's a factor. We don't care about it. Okay. So f prime is 2. The numerator prime is 1 times the denominator minus the top times the denominator prime, which is 1, divided by the denominator squared. So this is quite friendly. 2 x plus 3 minus x plus 1 over x plus 3 squared. Luckily, these two go away. 3 plus 1 is 4 times 2 is 8. We don't care about that. So this is our first derivative. Quite nice. Let's look at it and see whether f prime is 0. or is undefined where the function is defined? Is this undefined where the function is defined? Where is this undefined? At -3, but so is the function. So nothing there. Is this function 0? No, it can never be 0 because the numerator can never be 0. Now finally, please tell me what is the sign of this expression? Always positive. What does that mean about the function? When you say its derivative, it's always positive. It's always increasing. And now we're going to have to make sure that that's the case. Ready? From 2 to infinity, what does this function do? Is that true? From -infinity to -2/3 to 0 and to 2, what does this function do? Yes, all the time. Excellent. So the two rows appear to work well. Now I'm thinking of this, and that's my last step. So I will prepare the first derivative. So I'm not going to differentiate that. I refuse to do that. I'm going to say that the first derivative is 8 times x plus 3 to the, of course, make it as easy as possible. So then the second derivative will be -16 times x plus 3 to -3 times the inner function prime, which is 1. So I'm done. -16 over x plus 3 cubed. What I would like you to see is this. Because now I need to study the sign of this expression. And I'm not going to study the sign of this expression. Why am I not going to study the sign of that expression? It will be a waste of time. It's always positive. So from all this, only this with this will give us the sign. So it's -x minus 3, basically. It looks like this. So it's coming from positive going to negative. So coming from positive, at -3 will change sign and going to negative. Which means no inflection points. They don't exist because the function is not defined at those points. The function is not defined here. The function is not defined here. The second derivative is not 0 at those points or undefined. But since the function is not defined there, we cannot have an inflection point where it's undefined. Of course, it's not symmetric with a hole here and a vertical asymptote here. It's not symmetric, so I do have to write that. So I'll write it here. F of -x does not equal f of x, and it does not equal the opposite, so not symmetric. So now I will put everything together. I only care about the table. Nothing else matters. I will start with the asymptotes. I think this was obviously 11. I just want to check that yes. We start with asymptotes every time we graph a function. With asymptotes, we start with the asymptotes. So at -3, at +2, y equals 2, horizontal asymptote. Before we graph this, I just want to refresh your memory. A function is allowed and can cross the horizontal asymptote. It can. The horizontal asymptote has only one meaning. Way over there and way over there. Not in the middle. I cannot just graph a little piece over there and a little piece over here and say that's the horizontal asymptote. I'm going to graph the whole thing. But the function can cross it in the middle. Okay. But what a function will never cross is a right. That's not possible. Perfect. Okay, so now I'm going to plot what I have. I have 0, -2/3. 0, -2/3. I have 1, 0, but it's an open point. On this side, from 2 it goes to infinity, opening upward. It can be easier than that. Here it's coming from negative infinity, crossing the x-axis, going through this hole and approaching 2. Again, it cannot be easier than that. And this is f of x twice x squared minus 2x plus 1, the original function, over x minus 1, x plus 3. So what did we see in this function that we haven't seen before? We saw a hole and the vertical asymptote and horizontal asymptote. So every time you want to determine these two, remember it's a hole, it's a removable discontinuity. These two limits left and right have to be the same. That's why it's the same number on either side. So the function was always increasing, and it was opening downward from -3 to infinity, and opening upward from negative infinity to -3. Questions, please.